night. Today we have a half day. Afternoon, you're going to have a chance to visit things, hike, swim, do whatever you like. But we start the day with the French principle, discussing about state and parameters and the work earthquakes models. And I think we're not going to wait too long.
Thank you very much. I just wanted to do a sound check. So can the people online hear me? Because I think this is still muted. Yes, and there's no echo now.
It's not muted and the video, everything's on.
Yeah, everything's on, but I just unmuted and now I want to have Ian's trick of so hide view panel, that's right.
Hide floating meeting controls.
That's it, thanks. Okay, thanks, Heinz, for the introduction. My name is Femke Vossenpoel. I'm associate professor at TU Delft. And I realized that in this workshop, where should I stand in order to be? Should I stand here? No, because the camera is there. So I realized that a lot of this workshop is about algorithms, and yesterday we've seen some fascinating examples of that. Now, this is a disclaimer. I will not be showing any algorithms because the methods that I use are the ensemble common filter and the particle filter, and I think this audience roughly knows how these work. So there will be very little on the methodology, and it's really about applications. It's about the application of earthquake cycle forecasting, which is a domain where data simulation is not used a lot, so it's quite new. And it poses new challenges where I hope, as this is a workshop, to get some interesting feedback from you guys on how to solve certain issues or what methods to apply. What I'll show is not just my work, it's really the work of two PhD students and one postdoc working with me. I'll introduce them later on. But the three essential projects that I will talk about are, first of all, the state estimation in quite a complex seismothermal mechanical model, where we use the ensemble common filter. So we only estimate the state of that model, but we find out that it might actually be wise to also look at the parameters. And that's something we investigated in a much smaller model. It's called a Burridge-Napoff model. And when you see BK model later on, that's what it means. And then we also have a project where we apply real deformation data to actually look at the interseismic deformation, which is the deformation of the surface after an earthquake has happened. So that's just the overview of my talk. But first, let me tell you a bit why we're working on this topic. As you probably know, earthquakes cause a lot of damage, and I don't know the numbers for the worldwide financial consequences, but I do know that the Tohoku earthquake has cost us, as the society, $211 billion US. So that's quite a lot. And then for comparison, the work that I'm doing, or that we are doing, has been funded by, amongst others, Shell and the Dutch government in response to the damages that are happening in the Netherlands. And those damages are happening as a result of a gas explosion from the Groningen gas field, one of the largest gas fields in Europe. And the costs until now have been about $100 million US. So that's really a lot less than what earthquakes mean worldwide, but still worth the investment of a number of people to do more research into that. There is a large Dutch project that's called DeepNL. It involves 7 projects, 2 of which I'm involved with, and one of which I will be presenting today. earthquake physics. Let me start, give you a little bit of an introduction there, because I realized that many,
the online participants, they didn't see the full screen when you check. Is this full screen or not?
this is full screen, but I can double check.
Maybe you can just.
Oh, it says your screen sharing is paused. If I stop share and I share again, perhaps I will do it. And then I may just want to share my desktop rather than the application.
Now it looks better.
Now it looks better. Okay.
Well, actually now we can see exactly what you see behind you.
Yeah, so then I need to. I may want to. It's already maximized.
On the right, if you click.
Oh, yeah, then I can hide this. Yeah, no, but I was looking for that window of the Zoom. Yeah. There we go. So, Randy, can you
Well, you
check?
see the line, of course, in the bottom, but I guess.
Oh, yes, well.
That is okay.
Oh, well, I might be able if I do this. No. Well, you'll have to live with.
Yeah. Good
the
enough.
line. So this is an analytic model that computes the shear stress at the fault. And when the shear stress exceeds the strength, the fault will start to slip. And this is a very simple mechanical calculation that we can do analytically. And it helps us to know what pressure decline in an oil or gas reservoir would cause a change in stress large enough to make that fault slip. But for earthquakes, we don't just want to know when this fault slips, and also this is just an elastic computation. We also are interested in the plastic deformation. So for earthquakes, we work with more complex models. Against the control. Oh, there we go. And we actually want to compute the entire cycle. Now I realize that on the screen here in the room, the colors are very faint. Probably for the people on Zoom, the colors are a lot better. But I'll try to explain. Do I have a pointer? No, I'll just wait. All right, I need to use my mouse. So an earthquake typically nucleates at a certain point, and then there's a very quick moment in that earthquake cycle that the fault starts to slip. That's called the co-seismic phase. It's depicted here. And after that, we have the post-seismic, where it starts to recover. And then we have a very long interseismic phase. So this interseismic phase is a very long phase in which the fault yields. And after that, we can have another earthquake should the stresses increase again. So this is the cycle that we are trying to model with various models. Now, I'd like to start with the most complex model that I'll be showing you today. It's a seismothermal mechanical model. And as many of you know, ocean and atmosphere scientists, you would recognize the Navier-Stokes. So essentially what this model is based on is the Navier-Stokes equation plus the conservation of momentum. And by doing so, we can compute the stresses throughout the entire cube of our model. Now, what is really important is the stress at the surface that I showed you just before. So at this surface, let me explain how the cube is built up. So the cube is built up of two different blocks, where the top block is sliding over the bottom block. You can see the little arrows there. And that at that surface is where the actually fault is sliding. So that's the area that we're most interested in. And if we look there, we can model the friction at the surface with a so-called rate and state friction model. Now, I'm not going too much into the seismological details here, but I just want you to recognize that there are two relationships describing this stress, and that we have in the top relationship, we see coefficients A and B, where these are modeling the stick-slip behavior of that fault. So you, as I explained before, you have a very short phase in which the fault is slipping very quickly, and you have a longer phase where it's very slowly then recovering. And the coefficient A represents the direct effect, a very quick change, whereas the B is really used to model the evolution effect. And you'll see in more simplified models that this A and B is captured in a different relationship, and that's what I'm showing you here. This is the Burge Markov model that I'll be using for the second project that I'm demonstrating today, where the mathematicians amongst you may recognize a van der Pol oscillator, but we essentially have different variables. The U here is the slip, so that's the movement. The V is the slip rate, so the speed at which it moves. The theta is what the seismologists call the state variable, which describes whether the slip is moving fast or actually slow. And then the zeta that you see in the top line is actually a simplification of the A and B that I showed you before in a more complex model. And well, in the more complex model, we are doing state estimation. With this model, we'll be looking also at parameter estimation. So this is just to give you a flavor of the tools that I will be using in the rest of the presentation. But I also want to make clear that the objective of doing data simulation is to improve the forecasting skill of Earth cycle models. And this is a plot from Ilona van Winter, one of my co-authors, who was one of the first people to use data simulation in an earthquake cycle model. And what she demonstrated very nicely is that you can really improve forecast skill. Now, many of you may not be used to this type of diagram. It's called a Molchan diagram. And you can imagine that if you don't know anything, then one way to do earthquake predictions is to simply at every moment in time say there's an earthquake, there will be an earthquake coming. Okay, so if you do that, then your alarm duration is 1, because you're always sending a warning. Now, you're then, if that's the case, then you'll be, your failure to predict will be 0, because you told them there will be an earthquake. But now, if you have less warnings, you may have a complete failure. So you can imagine that this diagonal line from the top left to the bottom right, that's what you would have if you really don't know anything. Now, if we have a random model, we'll get at the black lines, but then if we use data simulation, we're actually arriving at the red lines. So in an ideal case, you would have a vertical line like this and a horizontal line like that. And Ilona showed that the more data simulation you do, the better you push that line down. So that explanation just to explain one single graph, but the point is that data simulation helps. So that's the work of Ilona, and I'll show in a minute the configuration that she used for her data simulation. But in Japan, there are 3 groups of authors, perhaps the most important one to mention, Hirahari and Nishi Kioi, who use data simulation also for earthquake forecasting. And both of these key papers discuss slow slip events. And what I have just been explaining about that earthquake cycle, you really have this very quick pro-seismic phase. But slow slip events are essentially similar events, but then moving much slower through that phase. And as they're more well-behaving, they're easier to simulate. So that is like a good starting point for this data simulation. And today I will show you the work of Hamed, who is actually extending this work to to faster slip, so earthquake events. Also worth mentioning is that the work of Ilona, my co-author, was only doing state estimation, so we're now exploring state and parameter estimation. And the work of Yohavi and Fiori is about state and parameter estimation. So what is the setup that Ilona and Hamed have used and will be using? On the left, you see, well, I think it's better if I stay here so people see me. On the left, you see a lab setup in Rome, where they have a subducting plate that's mimicked by a plate with sandpaper. And the region with sandpaper is where you have the seismogenic zone. So that's where actually the slip occurs. And it's the surface on top of that wedge is mimicked by a gel layer. And the fact that it's gel makes it very attractive for monitoring. So we can pretend that this is our Earth. It's a lot smaller, of course, but we can monitor whatever is happening by putting sensors in the gel or looking through the gel. So this model has been mimicked by this physical model has been mimicked by the numerical model. And in that numerical model, Ilona showed this improvement of her custom scale. Now, what we are doing at the moment in Utrecht and Delft with Montero is we use the data of a lab experiment in Tokyo. And that's at the National Research Institute for Earth Science and Disaster Prevention in Ibaraki, it's close to Tokyo. And it has been funded also by the NAM because they're old company in the Netherlands, they're very interested in induced earthquakes. And this setup is actually very much like the setup that I showed you earlier. There are two blocks, and those blocks are sliding. So by moving the top block, we can actually measure at the interface between the two blocks, and those will be the measurements that we will be using in the data and simulation. With this as an introduction on seismic cycles and on earthquake cycles, I really want to acknowledge my three co-authors. Hamed Montero, who's in the room and has a poster where he can explain more if you have questions. Amandita Barrier, the postdoc, she has left us because she's still working on completing her paper. And Celine Marsman, who is a PhD at Utrecht University. And they will, they're contributing to the points 2, 3, and 4 in my outline. So the first project is the project where Hamed is involved. And I just showed you that Japan experiments. And this scheme is showing you how the Japan experiment is modeled in a model configuration. And you see that blue line is the seismogenic zone where we actually want to know what's happening. Our measurements are not exactly on that zone, and you can imagine in reality we can never measure at the fault. So we have observations at the little red blocks where we collect both shear stress tau and slip velocity or velocity v. And the actual slip velocity sits at the blue line. We are really interested in knowing this seismic state, which is at the fault, so that's in the blue, and the shear stress at the fault, which we refer to as the hidden states because we don't have observations of that. Now, the approach that Hamed took in his data simulation work is he estimated shear stress velocity in this state. He ran an EnKF with 50 ensemble members. He used PDAF for that, so thanks to Lars Nerber for this wonderful tool. And he used the Garnet simulator, which is a simulator developed at ETH under the supervision of Ilona van Leet, who is also involved in this work. And Hamed has been simulating both slow slip events and earthquakes. And then the goal eventually is to mimic the lab experiments that I showed you in Japan. This is the workflow of an identical twin. I think for this audience, most people will know how an identical twin works. On the screen, it has very nice colors, but here it's a bit faded. The essence of the data simulation sits in the bottom two blocks, where on the left-hand side, we see how we generate the prior ensemble by perturbing the initial stress at default. And on the right, we see how we come to a posterior distribution. So that's referred to as the analysis step. And as we don't want to immediately start working with the actual lab data, we create synthetic data by running synthetic truth with this Garnet model that I referred to, and then sampling the observations at the predefined observation locations and at observation times. Oh, that's very kind of you. Thanks. Only the people online will not see that, but it's for me, it's very helpful. So there are two types of events that we've modeled. There's the slow slip events, which, as I said before, have quite a gradual slip. And there's the earthquakes where that slip event happens very quickly. Now, both of them do a reasonable job in matching the data or getting to the truth, but you can see that the co-seismic event, this very quick event, is really the challenge of getting it right. And that's demonstrated here why that's such a difficult period. We see that in the interseismic period, the behavior is very nice and gradual. So we have quite a nice, well, perhaps not Gaussian, but a unimodal distribution of our ensemble members, and the EnKF works perfectly fine. But at the moment of this earthquake, of this co-seismic event, for the slow slip, we still see a relatively nice behavior. But when we go to earthquake events, we see that this is actually becoming bimodal, because some of the ensemble members will still be at the high stress level, and some of them will have slipped and are at the lower level. So this is a challenge that we're currently addressing, and where it might actually be helpful to either the parameter estimation, so we pool the system in the right cycle, or where we use a method like particle flow, and that's what Mohammed is investigating. Now, just to re-emphasize how the observations are really putting the solutions very much to have a good solution in the interseismic period. These stars here mimic the observations, and not all observations are shown. The blue in the histograms along the axes, this is log velocity versus the shear stress. The blue indicates the prior, and then you see the green really pulls the prior to the posterior state. So we have quite a good fit in this interseismic period, but in the co-seismic period, we have virtually no observations. So it's very hard to really model that velocity in that co-seismic period. When we look at the shear stress, it tends to do a reasonable job, because there's a very good relationship between the shear stress in the medium and the shear stress at the fault. That was the last slide of the results I showed from Hamed. If you want to know more, you can talk to him with his poster. And just to demonstrate our end goal is these are measurements of that Japan experiment, where we have very different behaviors, so regime shifts in this earthquake cycle situation. And in principle, our model can model this, but then really being able to recover that behavior from the observations of the lab experiment, that will be the challenge that we're facing. Summarizing the results of this project, data simulation effectively improves the simulation. We find that shear stress observations really help to improve the shear stress, but velocity is much more tricky, and especially that co-seismic phase is difficult, and it's that short period, that very quick motion that makes it hard. And tests on synthetic twin experiment are now being extended to tests with laboratory data. And moving out to the second example, and I see that I should speed up a little bit. And this is a simpler study, but then a much more straightforward model. I mentioned the van der Pol equations, and you see here that in this Birch-Knopf model, we have three main variables, theta being the state, U being the slip, and V being the slip rate. And the behavior is very much governed by the friction parameter zeta in this case. So what I will be showing you is experiments where we introduce a bias in this zeta, because typically, and this is not only true for seismology, but also for oceanography and atmospheric sciences and subsurface applications, we don't know the parameters very well. So suppose we're thinking that this zeta has a value of 0.6, while it actually has a value of 0.7, then you will be working very hard to get that system out of this faster behavior into this slower behavior. So this is shown, I will be showing you more plots like this. This is showing shear stress against the state. And typically one earthquake cycle will be one cycle in this space. So we really need to move one system to the other. And this study is also meant to demonstrate what happens if you're only doing state estimation. Well, actually your parameter is wrong. Now, as I showed you before, this model is actually mimicking the behavior of a block that you pull with a string on a rough surface. And if you do that, you will see that the block first sticks, and then it slips, and then it sticks, and it slips. And that's quite a straightforward mechanical model to simulate earthquake behavior. Now, in this study, rather than using the EnKF, because it's such a small and tiny model, we played around with the particle filter. And as you may have noticed in my previous slide, we added the stochastic term to one of the mechanical equations, which means that when we resample, we automatically get different behavior for all of the particles. That's not always the case for subsurface models, as some are very deterministic. So we ran a particle filter. I don't think I need to explain this graph, assuming that particle filter is clear. We had 1,000 particles, and then we're updating the shear stress, the state variable, and the velocity. Those are state variables. And in the case of parameter and state estimation, we're also updating the friction parameter zeta. Now, this is what happens if you only do state estimation. And the red line here is the stereo mean of that particle filter. And you can see that it's struggling quite a bit to follow the truth, which is indicated here by the dotted lines. Even though we have very frequent assimilation steps, every 4 time steps, we have synthetic observations that we try to assimilate, but it simply struggles to fit that line. And what happens exactly is shown, it's illustrated here. The colors don't work out very well on this screen, but they're better on Zoom. We see that in our prior, most of the ensemble members or most of the particles will sit at will have already slipped because it's faster than what you expect from the true parameter. So many of the particles sit over here, whereas the few particles that sit over here are actually closer to the actual behavior of the right parameter. So by assigning weights in the particle filter, or computing the likelihoods, we're actually pushing up the weights of those particles relative to the particles below. And that's how we managed to, at least for this first cycle, to get a reasonable behavior. Now, if you were to compare this behavior with the EnKF, you see that in this first co-seismic phase, the EnKF simply fails to move the ensemble members to this true value, whereas the particle filter does manage to do that. We see, however, that at the second co-seismic phase, which happens at TS72, both the EnKF and the particle filter tend to fill. We see a little weight increase here for the members with a higher stress level, but it essentially demonstrates that just state estimation alone is not enough in this case. Demonstrating that again with the phase diagrams, where you can see that at this early co-seismic phase, we have particles both close to that stage of the true state of not yet slipping and that state where it has slipped. Whereas at 72, all the particles have already slipped. So there are simply no particles left at that slip moment. And when we do state and parameter estimation, you see that the variability in your particles becomes much better. And as a consequence, you really pick up this behavior. And as you're then also correcting the parameter towards the true parameter, you manage to find the behavior of that slip in that second earthquake cycle and the third and the fourth much better. So with this study, we demonstrated that actually the estimation of that zeta is converging, and it's so the 0.7 was the true value. And we see that even though we started with a value somewhere around 0.6, it really converged to the true value. So the state and parameter estimation in this case was quite successful. And with this case, we hope to demonstrate also to the more complex models that Hamed is working on, that just state estimation alone may not be enough. I still have 15 minutes. Yeah, so I think I'll summarize this here, and let me just check with you. I have the third project, but let me check so far if there are any questions on this part of the presentation. Let's see. No puzzled faces, so I presume that everything is more or less clear. Then moving to an experiment where we use real data. So I mentioned before we have the Groningen earthquakes, which are still relatively minor, but the Tohoku earthquake on 11th March 2011. Do I say it correctly? Well, anyway, it was March 2011. Was a major earthquake where we do have observations from GPS stations. And this is a very unique data set to see whether we can actually estimate some true interseismic deformation. Now, shown on the left is a map where I show the locations of all the available stations, and the colors here indicate the vertical rates. So as I showed you the earthquake cycle, it's veering up after the earthquake. And then we'll be looking in this study along this line shown here, this black line, and this is the actual fault indicated with the triangles. And wherever we have GPS stations is where there is land. So mind you, this part is C, and later on I will show you that the fact that we are also observing sea floor motion is really helpful in estimating the interseismic deformation. Now, just to indicate what one such a station observes, these are movements to the north, to the east, and vertical, and you see a bit of a seasonal cycle here. But in general, there's a northwestern trend indicated by these arrows, and you see some very slow movement in the vertical. Now, in order to model the deformation, we use quite a simplified static model for the position of the Earth's surface at a certain moment in time. Typically, after an earthquake, you see a bit of this bulging deformation, where we started to just fit a function to the observations available along that black line that I showed you before. And this behavior can be modeled with the equation that's given here that relates the density of the medium to the density of the air and the gravity constant. And then there are certain loads which you assume to be on the surface. Now, the solution of this equation is a Green's function. And in our data simulation, we essentially compute the coefficients of this Green's function. So we will be estimating, that's the thing to remember for you, we'll be estimating the Qs, which is the loads, the point loads on this surface. We will be estimating the H, which is the thickness of the layer, and we will be estimating the location of the point loads. And this is how that model looks like. I'd like you to focus on only the top part where you see this curve that we showed before. But then we have 2 point loads at Y1 and Y2. And that's where we apply the loads Q1 and Q2. And then depending on the thickness, which we can have vary from east to west with H1 and H2, you get different behavior. So by playing with the loads, having heavier loads or lighter loads, and playing with the thickness, we can actually model that deformation. Now, the experiments that I will be showing you are done with non-identical twin experiments. So rather than what Hamid was showing with creating data with one model and assimilating them into the same model, we're now creating data with a finite element model of the earthquake, and then using those data to fit the Green's functions model that we have. The objective then is to find the location and the amplitudes of the vertical loads, as well as reconstruct the plane thickness. We did this with a particle filter, and since this model is even quicker than the von der Pol equations, we use 10,000 members. So it's really a fantastic playground. And we tested it first with identical twin, then with non-identical twin, and in the end also with real data. The particle filter that we use here is similar to the particle filter that I showed you before, but because this model does not have a stochastic term, we apply jittering, and we didn't need to do this in order to maintain sufficient variability in our ensemble. And then using the data simulation like that, we were able to reconstruct the plate motion, both with one plate, that's the blue and the orange here, and for a 2-plate model. But we do see that when we have no C4 data, so that's the blue line here, it really struggles to find the deformation in the offshore part of our period. So we already figured from this that it's important to include the C4 data. Now, this is just a static model at one point in time where we simulated all data available at that point in time, but eventually we want to have the transient behavior of surface. So we are looking at applying that static model time and time again when the model, when the data arrive. And this is showing you 2 experiments. I won't go into details too much, but it's showing you 2 experiments, one with where the truth was a relatively thin layer and we had light loads, and one where the layer was relatively thick and we had heavy loads. And both of them seem to perform quite well. However, what we do find is that there's always the trade-off between the loads and the thickness. And you see that essentially solution space has so much freedom that you can find different combinations, and only by constraining the data to more physical values of H, we managed to get a good fit here. And that's also what I'm quickly going to show you what happened with real data. So this is the same as I showed before, but then a slightly more elaborate plot. Let me take you through it. So we have the thickness and we have the load estimation. And we start off with particles in this domain. So that's the prior is given in gray. And then as we move in time, you see that the solution, just like I showed in the previous slide, is gradually converging to one value. And that value coincides quite nicely with the true value in this case, but this is the synthetic experiment. The same is true for the location of the load and this is across both the location and the size of the load. Now, when we do the same trick but use the actual data, of course, we cannot show the truth in these plots because we don't know the plot. But one thing we observe is that, as with one of the synthetic experiments, the thickness really likes to go to very low values, even unphysical values. And we had to put a constraint here in order for it not to go to close to zero. And the load, it really likes the load to be low. Now, if we look at these results and we compare them with what we expect for the total earthquake, it really doesn't make sense. So this is still very much work in progress. But summing up, we did show that the particle filter is effective in estimating mechanical parameters. However, the model that we use here may be too simplified to model the total earthquake. As soon as we stay in the identical twin domain, the method works fine. The non-identical twin with the finite element model also seems to give reasonable results, but then when we work with real data, there are really a lot of processes which need to be explained. And this could, of course, also be that the GPS is measuring much more than just that interseismic deformation. So that was summing up the third project, but then I'd also like to say a few concluding words on the three projects that I showed you before. So in general, I dare to say that the simulation of limited borehole data, and in Hamet's experiment, we only had one point where we were observing, can improve the hidden states. I showed with the Van der Pol equations and the Burge-Nopov model that combined state and parameter estimation is definitely giving better results than only state estimation. And with the use of GPS data, we hope to be able to estimate geomechanical parameters. But I think I also demonstrated with these three projects that data simulation in seismic cycle modeling is still very much at its infancy. And for that reason, I'm very happy to present it to this audience, because I think many of you will have great ideas how to improve or how to work on these results. And I'm very open to your suggestions. So with that, I'd like to thank you. Oh, one more thing. Yeah. The work with the Burge-Nopov model is described in chapter 19 of this book, which I'm very proud to present. I was hoping to bring it with me, but I forgot it. So you all have to order it in order to feel the nice book. I'm really proud of this. I hope Gary is in the meeting. And it was really a pleasure to write this with Gary and Peter. So by all means, scan that code and it brings you to the PDF. It's open access, recommended to all your students. So this was my commercial break. With that, I'd like to thank you for your attention.
Yeah, so maybe I didn't understand. In the last experiments, were those particle filters you were using?
Yes.
Why was it moving to non-physical values? Was that the jittering that was doing that? Or I would have thought in a particle filter you don't.
It's always physical, yeah. So it was the well, first of all, it's real data, so we don't know whether with our collection of particles we're actually capturing the real situation. So it wanted us to move. So the real data were pushing us towards the edge of what we constructed, and we could have it move away, but then we would get values for the plate thickness that would really not make sense.
It looked like it moved out of the envelope.
It moved out of the envelope very much, yes. So that's why we're not pleased.
Okay.
So it essentially means that we chose. So we could get better results if we would choose different prior to start with, and then it may stay within the envelope. But then in a physical sense, the parameter values that we would have then would not make sense. So we're missing something in the model that's.
Yeah, no, I agree with that.
Yeah.
I just was surprised.
Well, we can talk more about it offline if you want. Yeah, Tom.
That's a very nice talk. Can you give us some comments on, so far I've seen many 1D.
Most of the results are 1D results. So what is your comments on 2D or 3D local and global seismology?
Yeah, that's a very important point, and Hamed will be pleased that you asked this question because he's currently working on a 3D model. So the model is there and he's able to simulate earthquakes, but he wants to tune it in such a way that it can represent the Japan lab data. And then once it gives similar behavior, we can start trying to assimilate those data. Personally, I have a bit of a concern on the non-linearity of the model and the fact that Hamed is still working with the ensemble common filter, because what we noticed in this post-seismic phase means that you may want to work with something that's able to deal with non-linear, non-Gaussian behavior. And for that reason, Hamed is diving into the particle flow at the moment. Hopefully that can help us out. Yeah. Well,
Thank you. I'm curious, so the periodicity of the signals you have, whether it's simulated data or this Rome gel experiment, is very striking. You have varying frequencies. So is that true, like in nature, or is it only because of the sandpaper that chose Rome?
that's indeed like the sandpaper in a lab experiment can be quite regular. In nature, we will seldom find this type of, because if it would be as regular as that, we could, the predicting would be, okay, just put your alarm clock. No, but that's a very fair point. So we're still, and in that sense, people argue, perhaps we will never be able to predict earthquakes, but then at least we would like to better understand the mechanisms responsible for earthquakes. So we can, but it's a very valid question. I forgot to mention it.
Thanks again.
Yeah, so if you have more questions, please have a coffee. Later.
The second speaker for this, Francisco Silva.
Yeah, then we have to switch the computer. It may take.
Yeah.
You talk about the bias.
Oh, sorry, that's the one you need. Yeah, and this one you need. The camera.
Thank you.
I think I can ask the hotel. Maybe they have some ways of going.
You can use your USB to.
Oh, we also control the slide from there.
Yeah.
Yeah.
Switch speed. Unmute. Is anyone unmuted in the online audience? Yeah, then yes. Please.
Okay, so good morning, everyone. And thank you, first of all, for being here and for your attention for this small presentation.
Today I'm going to talk about reduced basis ensemble-Kalman method or ensemble-Kalman inversion. So as you can see from the title, we have two main concepts here. One you're surely familiar with, which is the ensemble-Kalman inversion. And on the other side, we have reduced basis that are numerical techniques for the discretization of parabolic parametric partial differential equations. Actually, 4 partial differential equations, but in my study, we will deal with time-dependent problems of the parabolic nature. Before starting, let me, nope, it's on the other direction. Let me acknowledge my collaborators. There's a search I've been done with my advisor, Professor Karen Roy, with Cecilia Parentini, and with Martin Greppel, thanks to European funds. Let's start with the outline of what I'm going to say you today. So I'm going to have first 4 sections, which are more related to the algorithm. First, we will give an introduction, probably here unnecessary, but will give me the opportunity to establish a common rule for nomenclature. After that, we will describe how to treat with variational methods data simulation, particularly for unregularized problem, and I will pass through the ensemble-Kalman inversion or ensemble-Kalman method very briefly, because I expect all of you to be familiar with it. And then I will stop on model approximation, and I will try to combine the two. So let's start with a convention. I refer to synchronous data simulation. It's more or smoother than a filter. We are assuming that we have a set of data that comes from different locations in space and different times, and they are given by observation of the true state plus an additive noise. While on the other side, we have a model, a partial differential equation that here I formulated in this way that's probably unfamiliar for you and also for other communities. Was not a fortunate choice, but that this structure was chosen in order to stress the weak formulation of the problem, and then it will be useful to formulate a numerical approximation based on reduced basis. And as we are all familiar, the idea is to combine those two words to make an estimation both of the state and of the parameters entering in the model. Now, how this estimation can be done? Well, in deterministic approaches, use a variational data. One of the variational approaches consists in variational data simulation. It's related to, in this formulation, to a maximum likelihood estimation. And the problem is of minimizing the misfit between the actual data collected on the system and the data simulated, so observing a simulation of our system. It's in this formulation here written is a constrained optimization problem. Usually this can be joined, and so instead of L of U, we can have a H of the parameters mu, but if the model is non-linear in many circumstances, this passage is not easy. So more in general, I decided to choose this formulation. And now the idea is, how do we solve this problem that is often ill-posed? Well, one possible approach is including a stabilization regularization term, so a Tikhonov stabilization that has a strong duality with in Bayesian inference with the prior distribution through a minus of the probability distribution function. But the approach of ensemble-Kalman method is more of an irregularized method, where we use Langmuir iterations to resemble a final estimation. Yeah, the idea will be to apply on a fake dynamic, so with no dynamics, but assimilating the same data over and over, to have a process that approximates the likelihood function, so that if we look for its expectation value, and if the distribution is symmetric, so there are a lot of assumptions. Unfortunately, here we will be able to make a max likelihood estimation. There are different approaches. So here I already implied that we're going to use particle-based methods, but actually there are also other methods could be used, like local approaches, like gradient descent and the Newton-Types method. But here, for this context, it's definitely the best choice is to look at particle methods, and particularly to the Samuel-Kalman method. You are all familiar, so I can go very fast through. We have sample of particles with a constraint used to simulate the corresponding states and observation for each particle in the ensemble. The covariances are computed, and each particle is updated at each step. This implies the solution at the 0 step of a model, partial differential equation particularly. So let's stop for one moment and see first in an infinite dimensional case and later in the finite dimensional case how to deal and how to write this equation. So what first was described in his weak formulation in that strange notation, here I propose in his strong formulation. The boundary conditions are missing essentially for sake of simplicity. And we have a governing equation, so the parabolic equation, plus proper initial conditions. This can be weakified, so we can test this equation versus proper test functions in a proper space. And we have a set of test functions for the state evolving space and time and for the initial condition. Now, what we can see here is that we can collect the test function, defining a new test function, which is just the stack of the two spaces, let's see up C, and this belongs to a proper functional space, which again is just the product of the two spaces. And this allows us to rewrite the problem from this weak formulation, that's probably the more conventional, to the notation I decided to use before. Now, this is in the infinite dimensional case, but actually we cannot solve the problem in infinite dimensions. We have to introduce a simplification. How do we do it? Well, in numerics, one possible approach among other, like maybe you're familiar with finite differences, finite volumes. I'm sure you're also familiar with finite elements, and finite elements belongs to the class of methods derived from Petrov-Galerkin projections. So here we have the partial differential equation. We look for a solution that belongs to a proper finite dimensional space X epsilon, which is, since it's a proper method, embedded in the, or is a subset of the space X. And we test versus test function Ci, which also belongs to a finite dimensional space Y epsilon. And now the question is, we have these two spaces, X epsilon, so-called trial space that must ensure the accuracy of this reconstruction of the solution of the PE, and the test space, which must ensure the stability of the method. How do we choose these couples? Well, again, there are different methods. You might be familiar with the spectral methods, finite element methods. The idea of reduced basis methods consists of starting from a set of pre-computed solution and extracting the main features from that set in order to build very small dimensional spaces, X epsilon and Y epsilon. And for example, if the solution is analytical, it can be proven that the error in this numerical approximation decays exponentially with a number of basis functions, with respect to the, for example, classical convergence rate, which is a polynomial for finite elements of higher and higher order. Now, the problem is we are discretizing a model. The moment we discretize a model, we introduce intrinsic error with respect to the infinite dimensional solution. And this was the focus of my study. Probably for all of you who are more applied, it's the last of the problem, I expect, in the sense that there are many other sources of bias, of uncertainty, or miscapture physics in the models. But here I focused on this source. And so the idea is when we use the approximated model instead of the exact model, what does it change in the Samuel-Kalman inversion? And so if we start from the same starting point, we sample particles from a proper prior distribution. And then if in the Samuel-Kalman method, we computed the corresponding exact solution, here we just compute the approximated solution. If the Samuel-Kalman method, we computed the covariances, here again, nothing changes. We just compute the covariances employ the observation of the approximated state. Now we come to the analysis, to the update of the particle positions. And we might wonder if this was the rule to update the position of each particles. What do we do when we pass to the reduced basis, to the approximated model? Do we keep the same approach? And here, what we observe and what can be shown is that the answer is no, because if we use the same update, the minimization problem we would be solving would be the minimization problem involving the approximated solution. But if we expect our state to live in the space of the solution, to be a solution to the exact model, that would be wrong. That would lead at least to a miscalculation or a misestimation of the parameters. So we would like to modify this step in order to move from this minimization problem to the original minimization problem. How that can be done? Well, we'll not enter in details of derivation, but the idea is to treat the bias, the observation bias, so the difference between the observations of the solution of the exact model and the observation of the solution of the approximated model that we call observation bias, to treat it as a stochastic variable itself, which is at least initially distributed according to, say, push forward of the prior distribution of the parameters, and every step inherited the stochastic properties from the distribution of the particles. An idea then is that this bias, this observation bias, has its own mean and its own covariance, and it can be estimated from the observation of the approximated and exact model, and can be fitted into the update step, causing a translation in the data and further first inflation term. Now, what's probably clear to you is that if this was the approach, we would need to compute both the approximated solution and the exact solution at every step. So if our final goal from passing from a better model to a more coarse model, and I make this difference because I am assuming the infinite dimensional problem, well, we cannot solve that, while we could use a very accurate finite element discretization, or we could use a low dimensional projection with still a good accuracy, but with a larger error. And well, if we had to compute the finite element solution, the final cost would be exactly the same of using the original Ensemble-Kalman method. So the approximation we did is to rely on the estimation of those two momenta, just rely on the first distribution of the particles. And at least for the toy problem we treated, that led to at least an improvement, when not to a radical change, or essentially solution of the problem arising from the approximation. That's, I think, and you will see, will be the next example, mainly due to the naive nature of the problem itself. But at least shows that this can be an approach. That's concluded the algorithm part. Let's pass to the numerical experiments. We treated a very simple problem where we have an advection dispersion equation with an unknown diffusivity. There is an advection field which is given by 4 Taylor-Green vortices, and we have, as an initial condition, 3 radial compactly supported basis functions, and we are observing the state in 3 positions at 40 activation times. But the sensors and the activation times are no local, so they are average of a spatial region and over time interval. And we have the parameter set in a proper interval of that's needed for the construction of the reduced basis space. So for this problem, we first computed the solution using a finite element discretization with 10,000 degrees of freedom in space and 240 degrees of freedom in time. Here you see an example of the solution, and we consider this finite element discretization as the exact model. That means that the observation comes from the observation of those solutions plus an arbitrary Gaussian noise. Quite simple. Then we use the greedy POD algorithm for the construction of the reduced basis space. That means that from 10,000 degrees of freedom in space and 240 degrees of freedom in time, we moved to an epsilon degrees of freedom, which an epsilon is the number of the basis function in space, and still 240 degrees of freedom in time. Here you can observe the trend of the approximation error, so the maximum relative error over the interval of parameter I showed you before, as the number of basis functions increased. And as you can see, the trend is nearly exponential. And with already 42 basis functions, we obtain a pretty small error, 10 to the minus 3, which is possibly much lower than any. If that was a real case, the model would be exact and bias would definitely come from somewhere else. But here, since we are just restricted to this, our view was the only cause of bias in the data simulation problem. The advantage of passing from this finite element to the reduced basis model is the speed up. We have a speed up that is up to 200 times faster. And thanks to the fact that this employs error bounds, so we don't need to compute the finite element solutions everywhere to build this space. The training time is pretty fast, effective. It's just 2 minutes. So using this, combined with the ensemble common method, as described before, we try to make first an experiment studying the noise effects. We try to estimate the proper parameter 1/25, ranging over so from 10 to the minus 6 to 10 to the minus 1 to the minus 2 for the relative noise magnitude. We assume a prior distribution to sample the particles, which is a uniform distribution. And in order to account for this, to collect statistics on the possible realization of noise, we computed the experiment 64 times. So we iterated first time, the second time, the third time, and then we kept going. But here already you see that the method is converging to an estimation. And what we observe is that depending on the noise, well, if we use the reference full order model, so exactly the same model used to generate the data, as the error goes to, noise goes to 0, the relative error in estimation of parameter goes to 0. In this case, the trend is linear. On the other side, here I have to explain what here I call vanilla reduced basis method. So if we just take the classical ensemble common inversion and we substitute the exact model with an approximated model, what you observe is first region where the error decreases, where the error is in the estimation of the parameter is dominated by noise. And then we have a region where noise is so small that the error is dominated by the bias in the model. And that's essentially is a systematic error that cannot be removed. And that's why we have this saturation effect. And now if we implement the correction proposed, we are able to obtain a behavior that is at least as a trend in line with the one obtained using the full order our exact model. And with the advantage that the cost of a solution is just 4% of the cost of a full order estimation of the parameters. Another experiment we made was changing the reduced basis size, so changing the accuracy of the model. And well, if we just substitute the model with the exact model with approximated model, what we obtain is that as the reduced basis size is increased, the approximation error in the parameter estimation decreases, completely reasonable. As we increase the accuracy, we reduce the measurement bias. As we reduce the measurement bias, we are able to estimate better parameters. While if we use a correction, we essentially, in this simple case, I want again to stress, we remove this dependency, at least in this range. With more complex problem we treated, for example, nonlinear advection dispersion with a couple equations and so larger dimensional parametric space. What we observed and more nonlinearity. What you observe is that this is not anymore the case, but still in all the experiments, both involving initial conditions and parameter estimation, we have at least one order of magnitude in improvement in the estimation. Another plot I didn't show in this presentation, I think I want to refer to, was another experiment regarding ensemble size. We made experiments on the ensemble size, looking how fast they converge to the main field solution. And what you observe is that using a reduced basis model, so where the state lives in a smaller dimensional space, this transition is much faster. So if 60 particles are needed to have a stable estimation, while before the error increases as the number of particles decreases. Here, after 15, 20, or even I would say 15, if I remember correctly, particles, the behavior is already the mean field behavior. This concludes the presentation. The summary, so we introduced the reduced basis solver to improve the efficiency of the ensemble Kalman method. We adjusted the method to guarantee its robustness to model biases. And we tested it on linear 2D problems, the one I showed, and to a bit more advanced, a bit more complex, still academic problems. Yeah, we tested on those. And on the outlook, except for an extension or to time-dependent problem, so not just to asynchronous data simulation, another improvement is to employ the updated distribution of the particles to update the two figures of merit, the two mean and covariance of the data bias. So far, and so there are some problems with that, because as the ensemble localized, and since we just want to rely on solutions over the whole interval, we're going to have a lot of solutions that are far from the localization, from where is localized the likelihood. And so we are not really able to estimate at least the covariance properly, but we hope using some interpolation, some Gaussian process to be able to have a better estimation of those and so have even better results. This concludes the presentation. I decided to add some reference were useful for my research. And that's all. Thank you very much for your attention.
Time for questions.
No, but I'd like to get the vocabulary straight in my mind. So what you call bias is related to the change of discretization from a mesh to a continuous process, and that is I call that representation error.
Yeah. Okay.
Because it's how you represent the reality and how the observations are related to something that is discretized. So that usually is used with a random noise, and it has zero mean and a standard deviation that has to be calculated. But is that the essence of what you're doing?
Yeah, that's the sense of what I'm doing. Yes, and thank you very much also for the correction in name, because since I'm quite new, I've come from reduced basis. I'm still missing some of the.
That was all of my question.
It's not that you were first to my question, for the same question.
Representation error.
Sorry, I'm step outside, so I missed the part that you reduce that basis for the nonlinear problem. So this is the state estimation or parameter estimation that you're working on.
This is parameter estimation.
So how to the nonlinearity, which equations that you dealing with?
So the nonlinear, well, even with a linear problem, clearly estimation is nonlinear. But the nonlinear problem we deal with was so we had a nonlinear diffusion equation with a quadratic term into the Laplacian. And the resulting, that was described in the pressure field over a pathwise region, okay, and was inducing a flow and a non-homogeneous diffusivity.
Okay, so I got it, thanks. So how do you deal with, so do you have to assume R5 decomposition on the parameter or no?
So there I used a tensorization. So since the nonlinearity was polynomial, I built tensors and then I made projections with tensors. As I say, in general, it could be either too expensive because already the memory to store the tensor was quite large. What I would use, and I'm planning to use for the next experiments, is hyperreduction. So just select some quadrature points suitable for the basis functions and compute there the nonlinearity. And there are papers that, yeah, that prove that this proper selection leads to a good integration.
Yeah, because if you don't assume that the alpine composition type of things, then you actually don't reduce, right? Even though you reduce the dimension of the state, but then you still have to go up to the original dimension to do the simulation. So it's not quite a model reduction that way.
Exactly. So unless you use hyperreduction, you always add an integration problem, which is a finite element dimension. And so despite you're using a reduced basis space, at the end of the day, it comes with an align cost, which is a full order cost. So it's not reduced. Yeah, you're right.
Okay. You're doing the mode reduction, and then you usually when you do mode reduction, you like to go back to your maybe time scale to see how your parameters look like that. You do this translation.
Yeah. That like of course, the problem when you solve the reduced basis, it's solved for the coefficients of linear combination. But then we project back into the.
I don't think you've mentioned how the projection back was done.
Oh, okay, yeah. Yeah, sorry, probably to get it simple. The idea is we are projecting the problem. We are computing a solution which is in a small dimensional space, which are the combinations. But then each of those coefficients correspond to one of the basis functions. And since the idea is that the solution is expressed as a linear combination of those coefficients and the very large basis functions, and then is enough to make the linear combination of the basis function with the coefficients coming from the solution of the reduced basis model to obtain back the full order or a full order representation of the solution.
Thank you, Jan.
Thank you.
Last Thursday for the coffee break, so discussing estimation of soil organic profile in example.
Do you need a microphone?
If people can hear my voice.
Yeah, so as this is sorted out, just as a note that fittingly to a mathematical workshop, I have 0 equations here. So, yeah, thank you. Okay, yeah, so my name is Tony Visper, as we said. Hopefully people on the internet can hear me. And as a warning, pollen really hit me hard this morning, so I might sneeze. And one of the reasons I don't want to use the microphone is because someone will go deaf if I sneeze while wearing the microphone. So I'm from the Finnish Meteorological Institute, and as everyone would assume when talking to someone from the Climate Institute, is I'm going to talk about soil carbon. So a quick question here. How many people in this room have woken up one morning and thought about how much carbon is being allocated to the soil? Yeah, so you are not alone in this matter. Okay, so I just realized I'm going to use this one. So my talk is going to have 3 parts. One is to give the overview of the system that we're working with and the questions related to that. So as a little bit of a background on myself, I did my studies on the use of data assimilation in large-scale climate systems. I did my dissertation on using data assimilation methods in aerosol physics. I did my postdoc with forest climate interactions and the use of data assimilation methods there. And now I'm working with soil carbon. So first of all, my career is going down really fast. But, but secondly, while working with these questions on these very varying systems of scale, time, scope, and like that, the thing that I constantly keep coming up with is that the methods we're working here, and I think everyone in this room can agree with this, as much work with this, is that the methods are important, but every system has a set of unique questions you have to consider when you start thinking, hey, what are we want to do and everything like that. And it's important to isolate those questions before you really start thinking, what are the methods most ideal for this? What are the questions we need to go look at and everything like that. So the point of my discussion here is that the use of these methods in soil organic carbon I think the paper I published on it is the first time, at least in the way we used it, I could come across in anywhere that it's been done. So the thing I want to talk here is that what are the challenges regarding this particular system, especially because, as we already established, no one here has ever given a second thought about, about that question. What little has been done, or what we did, and so forth. And then what are our current plans on how to start resolving these different questions? Yeah, turns out I don't know how to use this. So anyway, so now vegetation, even if you haven't thought about carbon, soil carbon, you've probably thought about vegetation, or you've run into vegetation. And this is, for example, for the NASA side, and as you can see, the vegetation on the planet, on the terrestrial side is really highly represented here. And this was actually a surprisingly new thing, because it used to be considered that in the 90s and the beginning of the aughts, the kind of idea is that the only system that really matters is the rainforest. You've already probably heard like rainforest, the lungs of the earth, and they do matter. But in the aughts, there was this sudden realization when looking at the global carbon fluxes that actually the rainforests matter a lot, but so do northern hemisphere forests, like deciduous forests and everything like that. They actually serve a really outsized function on the system. Now, and this basically spurred this sudden, because turns out that the uncertainties in forest ecological models and vegetation dynamical models, they had a huge impact on climate projections. Like, so they're actually one of the really big uncertainty factors, even to this day. And so that spurred this kind of idea, like we need to look at for vegetation models. But then nobody really thought about the soil for ages. Like it was only like about 10 years ago that somebody actually realized that when we're looking at carbon being allocated into vegetation, plants don't live forever. So when that carbon basically grows and everything like that, it's not going to be there. Even those trees, if they're there for 100 years from now, they've lost a lot of carbon. They've lost a lot of leaves. They've lost, so there's this dynamic system of carbon being circled in it. And the vegetation plant, like the carbon being stored in vegetation, is either released back into the atmosphere as CO2, or then when it decomposes, it's being allocated in the soil. So then at this point, so, and at this point, suddenly people started having these questions, because up until this point, again, about 10 years ago, soil carbon models were really simple, because everyone was like, hey, there's the Century model, there's a couple of other models. They were like, hey, the only thing we need to do is we're interested how much there is at the moment. It doesn't, like it matters, but it kind of matters and so forth. And suddenly when thinking about this and when realizing, even though it's been there the whole time, how big of a part the soils play in that global carbon cycle, there was this realization that as the climate is changing, as those temperatures and environmental conditions change, when the vegetation conditions change, we actually need to also start being better at how we simulate the soil and how we project the state there. Now, of course, because we live in the society we live in, this also led to sudden realizations that, well, a lot of systems, the soil is crucial, but one of the biggest ones of those is, of course, agricultural systems. So when people farm and everything like that, or like even forests can be considered agricultural in that sense. But so there were, for practical purposes, for following, generally, like how is the, like what are the allocations and releases of different nations for soil carbon? So there was basically a mandate that, so, oh, by the way, so every country has to do currently a national greenhouse inventory, which is basically how much they're releasing carbon and how much they're storing carbon. There are different methods. And soils have to be a part of it. Those soil projections are really unreliable. This isn't, by the way, even being this, they just are. And then there was this idea that and it's an umbrella of the UN organization. I don't remember it's UN degree, but the idea was that when started looking at how much carbon there is in the soil, that was like, hey, if we basically just are able to increase the carbon allocation there by 4 per mil, we are actually really good, like in climate change system, which of course, like commercial sites, the commercial parties then going like, hey, by the way, this sounds really good. Because, so for example, if you buy something that promotes themselves as being carbon neutral, one of the ways they're doing it is that they're buying systems, or they're basically looking at projections of how much they're investing in situations where they reduce the release of carbon from the soil, but the kind of, or increased allocation of that. But again, and I'm not even going to go through all the challenges in it, those models and even our current understanding on it is really limited. And it becomes even more challenging because when we're talking about this kind of initiatives, or when we're talking about carbon credit markets, or anything like that, what matters is what is in 20 or 50 and 100 years, which again is a really fantastic projectional problem. So I've talked about how difficult it is, and to kind of really, well, here are the summing up what it is. I will really quickly go through all these 3 parts. So So when we talk about vegetation, so I didn't put, because there's a lot of people here with the background in climate or oceanography, you know the challenges in measuring those. I'm not saying this isn't a competition, even though I'm saying we would win, but it isn't a competition in that sense. So when we talk about measuring vegetation, it's really difficult, but there are a lot of ways to do it. There are people who go to the forest. I don't know if you've ever seen them with measurement sticks or like just waves and everything like that. We have some satellite data. The satellite data is actually really funny on it, but it's useful. But there's a lot of satellite products, but the satellite products are usually based on one measurement. So, for example, there was a talk, I thought about it yesterday. If you ever, for example, see someone constraining, they're saying like, we constrain these projections with both NPP and GPP measurements. They're constraining it with the same measurement essentially, because NPP is calculated from GPP measurements in satellite products. There are flux towers. Don't know if everyone's ever seen them. These great big towers in the middle of forest and everything like that. So there are numerous ways to measure vegetation. It's more challenging than climate. It's more challenging than even oceans, but there are. So when we go to soil, these are essentially the only measurements we have. We have someone going to the field, taking a sample of soil that's from some depth, or maybe a sensor of some sort. Yeah, this is what we got. There's no satellite measurement, because there's no satellite that will tell us in 1 meter of soil, this is how much carbon you have. There's no drone that we can fly where like, hey, this is how you're doing. So we get one location measurements of numerous, and we have to do those kinds of measurements. We have to do 10 of them per plot in order to get, because at this point we get to another fun part. It's as heterogeneous as it comes. So if you look at that system, and if you think about that the soil carbon is being produced by the amount of vegetation, because it is driven by the litter on the surface. If someone came to me and asked, hey, estimate to me, like, how do we measure how much carbon is on this field? Just planning that measuring program that we have our representative. And at this moment, and in this talk, I'm not even going to talk about roots, which is this another fascinating, fantastic part subject. So, yeah. This brings us, and it's kind of connected to what I discussed before, is that the modeling on soil organic carbon, it really only picked up steam about 10 years ago. And a lot of the prior models were these, and this is the model I use, where I work with. This is Yasso. This is actually developed by our institute. And we use, in soil organic carbon models, I've run it so much into the word first order dynamics, which is a loving term to say a linear model. But anyway, so And this is what a lot of these are. And the reason for it is actually that we know that we have an idea of what are the dynamics driving it. And there is, for example, this millennial that's really complicated dynamical model between different states. But we don't have the kinds of observations we would need to really constrain those processes. And where it becomes, and as an example of this, there's this, so this is Yasta. This is relatively simple. We have 5 pools. The ones that ethanol, water, acid, and insoluble, they basically represent what are the processes driving the decomposition of those. They move between the different boxes or released in the atmosphere. Then we have humus, which is long-lived carbon, so basically mineral associated or in peatlands, peatland associated. We have the later fall, which drives it. It's broken into the same kind of components, and we can drive it. So this is a really simplistic model. I'll admit it quite freely. Then there's mimics. That's this really, I really like it. It's this US model developed by Will Leader, which has microbial dynamics as this driver for it, and it allows a lot more complicated environmental drivers, complicated and like that. If I run these 2 models on a finished field, they give the same result. Like, so it's kind of a tricky thing at that moment to say, like, well, how do we say which one's better in that situation? Because we do not have the kinds of data to really either assess them or even constrain the processes. So, yeah. Then there's this thing that, and now we're starting to move what we're the subject in hand. Initial states for solar organic carbon models are essentially, I'm going to say, yeah, I can say this fairly certainly, they're impossible to measure, because a lot of those measurements that we get from the field, they're total carbon measurements. They say this is how much carbon we have in this 1 meter layer. But the models, for example, to go back, the model runs on these 5 boxes. This is the model state. We cannot get this from the measurement. We can get parts of it, we can make assumptions on it, so forth, but we cannot get this. And this is, and it's kind of a funny thing, because there's a little bit of a debate, like when we talk about future climate projections, and like on the terrestrial side, and what are the largest uncertainty drivers in it, there's a question, is it the initial state or is it the climate? Because the climate is essentially the one driving the environmental conditions 100 years ago, and a lot of these systems have changed, so that should ultimately be the one determining what it is then. But the initial states are basically how we determine how different environmental conditions drive the system, and we don't have a reliable estimate of the initial state. And yeah, and again, if you go back and think about when I was discussing the climate, like the carbon credit cycles, it's kind of tricky for us to basically say we're gonna improve this much, how much carbon there is in the soil, when we cannot really say reliably how much carbon is there currently in the soil. So yeah, now, so when I started on this project and when I came on it, one of the things I did find interesting is, well, this is kind of it feels like this is an ideal situation. Like this is what state data assimilation is made. We have these challenging observations. We have these systems that are limited and like that. So then the question was, okay, can we use state data assimilation methods to improve this? And we did a really preliminary study on this. And we looked at just decomposition. So this was a part of this experiment that was done for the 1930s to the 1940s. They had 6 plus actually 7, but the data from the 7th is weird. Across Europe, Sweden, Norway, Netherlands, France, and they removed all the vegetation from the surface. They just went like, and they kept it removed. They removed all weeds and so forth. And then there wasn't no unified measurement. They just like sometimes went and measured it and sometimes, and then we got this time series from that. And that's one of the best, at least in my opinion, one of the best soil organic carbon related time series that there is. So we tested it using the ASTA model, and then there's some adjustment summer filter that Ian talked about yesterday, like as a part of DART. We actually ran the DART algorithm for this. And we looked at, okay, if we use state data assimilation compared to the regular YASO, because the regular YASO does actually pretty okay with this data set. We looked at like, okay, how do we get it to improve? And this was how, to give an example of how nightmarish the initialization of it is. This is the process we had to do the initialization. We basically assumed like, oh, 100 years ago, it was a forest. As a forest, it had this much litter fall. Then it got switched to agriculture. It got this much litter fall, and now we're basically removing all of it. So as you can imagine, the uncertainty related to the initial state is just massive. So we ran it then. These are the 6 plots we ran it with. The dark dash line is just a model without state data assimilation. We did a comparison. The red line is if we didn't do inflation, and then the blue line is the 25% inflation. And the uncertainty range is the envelopes. You don't really see them that much here. So overall, like this is the basic test. Do we actually see any improvement? If we, so this is at each measurement time, that's the project model prediction on that measurement time. And now some of you may have noticed, Rignon, Rosta, Moulton, and Versal go pretty well. OSCO sites have discontinuities. And this is again a fun thing about this data set. We don't know why it has discontinuities, but if you look at, for example, OSCO B around 1975, you suddenly see a massive drop in the soil organic carbon. In OSCO B4, you actually see it at 1965, and then you see a smaller one at 1970. So they're there, and the thing that made it funny was the ASCO sites show how important. So there, the measurements are every year. With the other ones, it's every decade, every 5 years. They're uneven intervals. But the OSCO sites show that the inflation method had to be used with the more frequent measurements, because otherwise the system dynamics are so slow that it's going to just drive the uncertainty to 0 and filter divergence all day, every day. But what made it funny was that then we looked at, because if we're thinking about the future, we will not have measurements from the future. So we looked at how quickly, if we just include the measurements, do we actually start seeing an improvement? And in all the systems, we actually, within the force measurements, we ended up getting meaningful improvements. Because, for example, even Versailles, which looks small, but it's partially because the y-axis is what it is, we got an improvement of 1 ton of carbon per hectare, which is really mean, like that's a lot of carbon. Like that's the kind of an improvement that matters for the systems we were talking about. But the fun part was that in the OSCO sites, we actually saw that it did worse with data assimilation because of those discontinuities. So, and we can't, for example, say that is there in Versailles, is there a similar kind of discontinuity, because we don't have the same kind of frequency of measurements. So, but then also going to the ASCO sites, as I mentioned, like when we did the inflation, it was able to adjust to the discontinuity, which is again what state data assimilation is supposed to do. And I'm not going to go too deeply into this because this is system specific, but we realized looking at the data in itself that when it corrects, because of the error covariances it creates with the system, when it creates the humus, it has an opposite reaction to the active pools, which is realistic because of the system it creates. But this should not happen, like, because this basically means that it's suddenly like our state data assimilation got it right, but when we run it just like this, it's suddenly like there's no litter in the system, but suddenly decides there's actually fresh litter happening, decomposition happening again. And this is purely because of the error covariance of the system. So again, the error covariance structures need to be reconsidered, but they're also kind of crucial. Because the error covariance systems are crucial, and I forgot to say this, we do not, as mentioned, we do not have individual measurements from these individual pools. We just have total carbon. So our update has to be that we compare to the total carbon measurements, the error covariance is transfer the data of these individual pools. It works well, but in this situation, it can also create an unrealistic system. So, as said, this was an initial test, a really positive test, but there was a lot to be done. Even beyond the questions we had those, in actual agricultural systems, we're going to have litter fall. And this is one of the big issues in the system, in that we have one measurement, which is the soil organic carbon, usually just the total. And it's essentially driven by two factors: the total soil carbon, like the previous soil carbon, and the litter fall. And the litter fall is tricky because there's a lot of assumptions on how it's used to drive. Like, for example, a lot of soil organic carbon use NPP, because the idea is that if you have a stable system, the amount of carbon you have allocated in that system then has to also be removed from the system. But there's a tricky part in that, because how you divide that NPP actually matters a lot. So because the more NPP you have in the roots actually contribute more to the soil carbon allocation than the ones you have on the surface. But there's no measurements to really say, like, it's really difficult to weigh with different vegetation or different plants how much of that is in the roots and how much is that in the surface. So litter fall is also a variable that we could update with state data assimilation, but we have to basically make a decision: do we update litter fall or do we update the initial state? Because we can do both. Yeah, and we also want, of course, and all the other things mentioned here. Now, our main focus at the moment, and this is because everything I discussed already wasn't complicated enough, is agricultural systems, which are not continuous, because when we're talking about carbon markets, we are basically have a bunch of farmers asking us, if we do these kinds of measurements, how does it impact the system? And the fields are not next to each other, and there's no, and in the middle, so for example, if we are looking at these two farms, nothing is being done in the forest in the middle of it. So we just have, so we have interest is like what is happening at farm 2, and for example, can we use that to improve the estimates at farm 1? And this is again kind of going good, because when we look at the system, we don't have infinite resources. They're not going to go into every farm and do measurements every year. So the question, for example, we have is, so how often do we need to do measurements at farm 1? At what intervals, at what times, and how helpful are it at farm 1 and 2? So yeah, so we are at the moment looking at these kinds of questions and essentially trying to figure out how do we approach this with state data assimilation. And we are setting up an offset system, which, as anyone we've already talked a lot about synthetic observations, and they've been mentioned here. As anyone who deals with those systems, that they're really helpful, but you have to be really careful when setting them up, because you can otherwise get really unrealistic systems. But for us, this is even more because we have collaborations with business side, and they, for example, have a question like, so by the way, how often should we go and measure it? And we don't have those kinds of measurements because they haven't been done. So we have to set up with this with the thought of telling our collaborators, well, this is the ideal frequency, and this is, if you have 30,000 euros, this is how you should spend it on the measurements. Okay, I will also end up on an advertisement, but I will not advertise a book I wrote because I have not written a book. But anyway, otherwise I would stop every single presentation I've ever done on that. So we have, well, actually 3 positions opening in our group, but two related to this. So we are now got funding to really start addressing these issues. And we have one person, Julius, we are working it on the vegetation model side. I'm working it on the solar organic carbon model side. So we have postdoc or PhD student level positions opening. FMI, great place. Forget everything I've said about FMI to the people I talked to, a really great place. So if you know of anyone who might be interested in this or in this position, please let them know. They opened just today. I just checked, checked them today. They're open. So if you just Google Finnish Meteorologists Institute open positions, you get those applications. You can send an email to me. Deadline is June 13th. With that, I thank you for your attention.
One of the questions, and then we can one question, and then we can talk to the
Just a quick question. So the mass of soil in the earth is clearly important parameter. At least if you want to think about the earth system.
Yeah.
But how do you treat them as a constant or?
So that's a really good question. So when we have the measurements, like there's kind of two different kinds of soil organic carbon measurements. One is the density of it. So how much there's soil organic carbon per certain amount of earth mass. And one is total. And a lot of the measurements are the relative amount, so the densities, but they usually don't have the density of the earth or the mass of the actual earth that they're using on it. So we usually, if we have the measurement of the earth density or earth mass, we use that. Otherwise, we have to make an assumption. Like, yeah, we use one.
You don't treat it as something that you will update in the future.
It would require different measurements.
I think, sorry, maybe you can discuss after that, because we are thinking to use the break time to take a photo group, so we don't have to waste time, before lunch. Otherwise, they have to wait us and then serve us.
So, but then we will not use the entire break for that.
Yeah.
So now it's very important that all of you go outside this window immediately, and we will take a picture, and then we can discuss it. Okay?
Thanks for the speakers.
Thanks for that.
Let's go. I start with a tough slide. So this is the very first slide, which is the toughest on the mathematical perspective. So the following ones are easier. So, and I think you're still awake after the coffee, so that should be fine. Okay, so the title of the talk is shading. So what is shading? So the shading actually starts from continuous dynamical systems and then further on with numerical discretizations. And in particular, I look at the shading from the point of view of numerical discretization, because by the training, I'm actually numerical analyst. So what the shading can be used is actually to look at the global errors of a numerical discretization if we have a chaotic system. Because we all know that if you have a chaotic system, then this is very sensitive to initial conditions. And if we start with a classical numerical errors, then that doesn't actually help us, because any initial error will grow exponentially. So it doesn't really matter what type of numerical discretization we use. However, a Shading approach to analysis of numerical discretization can tell us something about a tractor, whether we actually estimate an attractor value with a numerical discretization. So this is how I'm going to look at the shading, right? So the shading, so let's have this phi, Tm is a flow. So Tm is a time step, right? So this is a discrete time step, and phi is a flow, but typically you can think of a numerical discretization, right? So you have a scheme, you have a dynamical system, that is the derivative of that is some nonlinear function of that. You start with the initial condition, and this phi Tn is a numerical discretization, so it equals space and time, right? So this is in general, right? And then so we have this discrete time and also discrete state, right? So this discrete RF. So what Shading and Lemma specifically for numerical discretization, and this is dated to 1995, what it says that actually there exists a true orbit, so this discrete true orbit, such that this relationship is exact, right? So if you think in terms of the model error, there is no model error. So we just have exact solution. And this true solution, which is exact solution of the system, is different from an approximation, this UN, just by delta, which delta is a small, right? In some norm. And what is UN is called an epsilon pseudo-orbit. So that means it's actually, this is not exact solution of the system, however, is up to some epsilon error, right? So then if you think this is kind of a model error. So in the sense, we have some true trajectory that satisfies exactly the solution, and there will be an approximation that is not that far from the trajectory. So, right? And the Shadowing lemma that guarantees actually this is an existence of a solution. So if you think now in terms of a data simulation, so what we want to do, there is a true solution that we don't know of. However, we would like to find an approximation that is not that far away from the true solution. Right? So this is akin to a data simulation. Yes.
Clarify one thing. This is true solution. It's not true. It's not the true solution of
The original dynamical system, right?
This is still in the numerical sense, right?
Okay.
So this is, yeah, so this would be a numerical discretization, right? So you don't have an exact solution of the dynamical system of the numerical. And this would be a non-exact, right? So this is not about going back to the continuous systems, right? So this is really, you look at the discrete level, right? Okay. Okay, so this is already mentioned that basically the shadowing idea to data simulation, and I'm going to cite, so this is a paper of Kevin Judd and Lenny Smith from 2001, is that we have basically noisy observations, these are the red dots, and what we would like to do is that, and this is an attractor, right? So we have a just two-dimensional system, so I plot X and Y, so I plot an attractor. And we have these red dots, so these are the observations. And what we like to do with the shadowing is that we denoise them such that we have these blue dots, so we recover that chunk. So this has been done from 2001. So these are the authors that work. So these are the people who worked on the shadowing. So this was pioneered by Kevin Judd and Lenny Smith, but at the same time, independently, it actually was in another paper by Jochen Brocker and Paralys in 2001. So they were just working independently on the same approach. And there was a continuation in the same direction for the shadowing, the data simulation. All right. So how is it done? And we actually already saw today somebody talking about Newton type methods, about iterative methods. Right, so this is basically the idea that we define a function g that is a difference between the state at the n+1 step and the map that maps the previous time step to the next one. So if this is a 0, then we have the exact solution of the model. And if it's non-zero, then we have a pseudo trajectory. And what the Shannon methods do, they use an iterative method to actually find a solution, a 0 of this function g. Right, and then what you do just by iteration, right? You have this delta will be defined later. So you just iterate. So this is very important, that actually shadowing doesn't come from data estimation, it comes from numerical discretization. And we actually need to initiate the method with full observations. So we don't need to observe every time step, however, in space, we have to observe everything. And this is, of course, a limitation because the data simulation is about having sparse observation, right? Not full observation and actually recover the things that we didn't observe. But anyway, this is where we're going like historically, right? Just retrospectively. So we initiate this full observation, and this observation, right? This is a data simulation typically, or typically here you have an H, right? So because it's initialized at the full observation, this is the identity, and it's noisy. And the noise comes from a normal distribution, this mean zero mean and covariance matrix. And then this true solution is the exact solution of the discrete system. All right. Okay, so about this delta, right? So there are different iterative methods. So if you look at the work of Lenny Smith and Kevin Judd, they looked at this type of iterative methods where this P is actually Jacobian over G, and they suggest that there should be some gamma. And in these two papers, they could show that gamma has a large impact on the convergence, and they couldn't say mathematically how to choose this, but they actually showed that choosing this gamma is very important to have a convergence. And in this paper, delta is a more complex form. There is again the Jacobian, but there is some lambda matrix. And again, in this paper, it was not really clear. It was clear that this particular choice of lambda helped in the convergence, but it was not really clear whether other choices would help and how to actually make these choices. And in this paper, we looked at this type of iteration, which is, if you look at this form, is a pseudo inverse of a matrix T. And this works very well if you have a very good initial guess, because this is a really Newton method. But still, all of these methods are initiated at full observation or a proxy. And a proxy would mean that you have partial observation, you take your favorite data simulation method, such as, for example, ensemble, Kalman filter, or variational. You can construct an estimator from that, and you plug it in the shading. So that means like you would have actually two data simulation schemes, which again is not ideal. All right. So what I'm going to present today is that we actually got rid of this requirement of having either full observation or proxy of observations. And what we did, we said, okay, let's actually still have this iterative method, but we choose this delta in such a complicated form. And what is important to see here, there is the alpha, which is a regularization parameter, and this comes a lot in the regularized methods. So that's the same idea that's in the regularized methods in your program. So anyway, so this Q plays a role of model error, right? So you could think that this is Q is the matrix that represents the model error, and there is a sigma. And what had appeared is that the sigma, the choice of sigma, is actually very important to have a solution that is close to the solution from which the observations were generated. Right? And this is what we want. We actually want to have an estimate that is close to the true trajectory. And by true trajectory now, I mean the trajectory from which the observations come. All right. And for initial guess, we have partial observations. So we have some partial observations, right? Noisy. And anywhere where we do not have any observation, we just plug in a background trajectory. And this is a solution of a discrete system with arbitrary initial condition. So this is not something that comes from a previous data simulation scheme, not related to the observation, right? You could also think, well, this was my best initial guess, and I propagated forward in time. This is my estimate, and I use it. And these are the references that we took for the inspiration to come up with this form. And actually, the rest of this talk is about, a summary of this thing. Okay. So what we proved two theorems. The first theorem is actually there are under some conditions on the initial guess, and what is important on this regularization parameter alpha, what we can have is that we have a convergence to the solution manifold. So that means that this would be less than epsilon. This theorem one doesn't say us how close we get to the true solution, which is from which the observations are generated. So it only tells us we will get to a solution of the discrete dynamical system, which is also a good thing, of course, because then we will have also the all physical laws intact. And another theorem, the theorem 2, is actually says that the Shadon-based estimate, when projected on the observation space, so on this sparse observation space, it will actually remain in the ball, which is centered at the observations and has a radius of the observation error. So that means that the state that we observe will not go far away from the observation. Right? So this is where we will say is actually defined by the observation error. So if you have a very, very accurate observation, then this in the observation space, we will not be far away with our estimate. But what does it mean, this under some conditions? I'm not going to put any mathematical formula so you can find it in the paper, but practically what it means that in order to fulfill this theorem number 2, we need to actually choose a specific precondition in sigma. So this is the sigma, right? So that choice actually is really essential that we have an estimate that is close to the true trajectory. I think you had a question, no? All right. Okay, right. So certainly, yeah, looking at historically, actually all of these methods which were done in the past and this one, the theorem number 1, written of course for different deltas, actually will tell us that we have a convergence to the solution of the pole. So all of them, they satisfy this convergence. And only the theorem number 2, specifically for this iteration, actually tells us that there is a good estimation of the true solution from which the observation was generated. All right. So now I'm going to do some show some numerical experiments. So this is the Lorentz system. So Lorentz 26. So we observe every second variable in the Lorentz system, and we have observation of every 6 hours over 25 days, and we have a very large observation error. So this is typically this is 1 or 2 that we have. So what am I showing? So this on the right plot, I'm showing a model error. So model error is defined as the difference between the state at n+1 minus the map. Right, and the theorem number 1 tells us that this norm, this model error should go to 0 as the iteration goes to infinity. So this is what we see, and then what I actually chose, the sigma, the preconditioning, I chose it such that it either satisfies the theorem number 2 or does not satisfy. The theorem number 1 is always satisfied, so that's why I have this class. So you see is that if I have the theorem number 2 satisfied, so then this is the line that actually I have a convergence to the manifold very quickly. And when I do not satisfy the theorem number 2, the convergence is slower. So if I iterate for longer, they will both converge, but I just stop iteration. So now if you look at the cost function, and to compute both the model error and the cost function, we do not have to have access at the true solution, right? We only have, this is the model equation that I given, and this is the state and the observation they also given, right? So we can compute the cost function. So this is the observation error. And so when we see that if you do not satisfy the theorem number 2, so the all initial guess starts over there, we quickly go above the radius of the observation error and go up. So that means that we actually move far away, too quickly far away from the true estimate, and we obtain another estimate that has nothing to do with observation. So, and if you satisfy the theorem number 2, we actually see that we have a slower convergence but we stay in the ball, right? So we stay below this observation error. And so we do not exceed. We stay in the ball center of observation, and we do not exceed the radius of the ball. So what does it mean with respect to the error, Rudman square error? And now I plot observation, the error with respect to the true solution, right? So this is a synthetic experiment, so I know both of them. I mean, I know the state, so I just plot error of observed components, of non-observed components. And then basically what we see that if you have if you satisfy the theorem number 2, then the error of both observed and non-observed components goes down as the iteration proceeds. While if you do not satisfy this theorem number 2, then actually the error decreases over the iteration. Okay, so now if I compare it to other data simulation methods, and I'm going to look at the big constraint variational method and also PDA. So it's a method of Kevin Judd and Lenny Smith. So the one of the original ones. So then what we see the shading. So this is the errors of the observed component and non-observed component as a function of time. And so this is the bottom line. And we also did 100 experiments with different initial conditions, etc., different error realizations through trajectories. And so this gray line, the black and gray shaded area, is for the errors for the shading for observed and non-observed components. And we see that this is the lowest one. While if you compare it to the V constraint, this is above, and the actually PDA is really worse. But the PDA, why it's worse, because we need to have not just partial observation, so we need to actually pre-process them to have a pseudo observation. So it is well known that actually any of these previous methods would not work with this type of partial observations. But this is good that we're actually doing better than variational data simulation. Okay. Yeah, and I'm going to go quickly for the last part. So what we wanted to do is that we wanted to see whether we can do this method in the different subspaces. Right, so there is this partitioning of the tangent space into stable, neutral, and unstable subspaces, right? And then having this assimilation in unstable subspace. And well, these are the papers, right, that actually did consider the assimilation in unstable subspace. So, for example, Bolivar out is a well-known method, right? And there is also projected ensemble Kalman filter. So we wanted to do the same thing for the shading time method. Right? So this I'm going to, so we did the splitting, and then in non-stable subspace, so we did the shading based data simulation. And in the stable subspace, we use a rather cheap method that is called the synchronization. I'm not going to go into details about that. Just, you know, for the sake of time, I just mentioned that this is a synchronization that we use. All right. So basically, this plot, again, we were considering toy models, right? So this is again Lorentz model, Lorentz 96. And you can see that depending on the dimension of the projection, so this is error, and this P is the dimension on which the method is projected, right? So if you have a rather small dimension of the projection, then the error actually over time does not decrease at all. But once we start increase the dimension, then we actually have a better and better error decrease, right? And this is really has to do something with the number of positive, negative, and zero Lyapunov exponents, right? So, okay, this is what we did. So we said, okay, let's take our scheduling method for partial observation and plug in also extend it to the projected spaces and still do the Lorentz 96 model. And now we again look at the errors with respect to observed component and non-observed. So this blue curve that is above, this is the same variational data simulation, and this projected shading still outperforms it. So this is still below. This is here. And now if you look at the errors of non-observed components, they actually became in the similar way. So we are not outperforming shading and are not doing worse than that. So this is, I think, a good message. And I must say that we still don't know why this, I mean, we do know why this happened just because we observed. So in all theory, it actually tells us that everything you observe, you will actually stay in the radius. And here we will not have any control. Okay. All right. Well, these are the conclusions. Basically, we can have now Shannon method this partial observation, no need to have any type of preprocessing. We can also extend it to having a simulation in non-stable subspaces. So we did toy numerical experiments, and you're welcome to look at this paper. And thank you for the attention.
Good on time. We have time for 2 questions, I guess. People have many questions. Yes.
Can you go to the first slide again? I'm still confused with the things. Because you must have some assumption on phi, right? Because if phi is 1-to-1 invertible, then I only have unique solution there, and that field is not useful.
Oh, definitely on the phi you have so the shading actually like the So so what you can have, this is on not only on phi but also on the Jacobian of that. You actually have to have like the like a normal Jacobian has to be, you know, scaled in some, so some specific norm has to be less than 1, so that you have actually convergent subsequence. Right, so this is I would say not just only on the phi but also on the Jacobian of phi, right?
The Jacobian of phi is
yeah,
just part of
exactly.
the regularity of phi, right?
Exactly. So it's not for any, right? Because that's why I was saying, like, okay, there I skipped this condition. This is okay. So this is not for any dynamical system, even of numerical, right? There are some conditions under which it actually holds. It's not a general period. Yes, you're right. So this is right. If you read it like this, it seems like this is for any phi, for any f, right? No, certainly not, right? You have a very, and this is actually very strong condition, but typically what it boils down is that actually that you have an attractor, right? So you have a low dimensional manifold that you should be able to reconstruct from noisy observation. If you do not have an attractor, then basically that won't help. This is where the dynamical systems come into play.
All right, thanks. Can you go to the slide where you have 4 methods, including your, where you have a sigma and q?
I think this one.
Okay, this is the one. So for the first 3 methods, so in this type of setting, P must have a full row range because otherwise it's not invertible.
Yeah, exactly right.
So
So yeah, so the right because so yeah, so this is what they do, right? I mean, like in the method 3, this is the pseudo inverse, this P transpose P transpose -1, right? So then you actually do this kind of, you can have like this type of inversion. While in the method 1 and 2, if you look at, so what helps is that you have the numerical discretization as an explicit numerical discretization. Then actually what you will have that the Jacobian would be fat and short, and then you will have, well, I need to think, like you do the fat and short times tall and skinny, so then you get a full rank matrix, right? Right? So yeah, so that's the trick that you need to do. Or you have to have, like in the method 2, you have to have some metrics that actually helps you with low rank problem, right?
Yes, it's only method and your method. So it sounds like you have to introduce like alpha and Q and sigma, something like, how do you, my question is, how do I choose the best of it? What's the best choice of?
Exactly.
alpha
Right?
and
So this
sigma?
is, so in the paper, we actually explain, so the Q doesn't, at least, okay, the Q doesn't matter actually, apparently. You can choose anything. So the choice of alpha then matters because the alpha actually depends on the Q and then the sigma and then the P. So there is actually a formula how you can choose an alpha such that you have a convergent method, right? So you really need to look. So if you start with a given P and a given Q, then in a given sigma, then you can compute from that what alpha should be. And then actually this sigma, you can also, with the sigma, you actually introduce, you can also introduce a prescaler. And with this prescaler, basically that will tell you how you move up and down. And you simply look at the errors, whether this is go up or below the observation error.
Alpha is I think easy, but sigma is unfair because the matrix, right? It's also depend on the dynamical system. So it's not clear on, I mean, what is your instruction on how to apply a matrix sigma?
So what we did for this experiment, again, this is just, this is a Lorentz system. So what we did, we said that the sigma had actually was, I think what is even an identity matrix with a scalar, and that scalar you actually tune, right? So you choose one and you see what happens to the observation, to the cost function, whether it's up or down, and then you go from there, right? You tune it less or more, and then you see how this changes depending on the cost function. And this is of course not nice thing because you don't have to be in a twin experiment setup, right? Because this is the observation, and this is the state projected to the observation space.
I think you look at the watch, so I think it's right now. But I'm interested in more on general sigma identity is so easy that they have only one scalar, right? But in general, the matrix, how would you want to do it? But let's talk about it.
All right, thank you.
We can also do a question to Francesco.
Okay, can you go to the next slide, please? Oh, no, the one again with the 4 options.
Yeah.
This one. So if I understood correctly, here for initial initialization of U, which is a collection of states, it gets a iterate and you convert to a sequence of states that lie on the transfer. But I didn't get what rules place the data on this.
So this is your initial guess, right? Mm-hmm. That's the only way where the actual data enters in the method, right? It never enters in any cost function anywhere. It only starts as the initial guess. That's why you could move away from it, right? Because you do not constrain with your cost function, right? That you need to be close to the observation. So, but the whole idea of the shading is that actually that you get the attractor, and then the data that you have is just the initial guess, right? This is quite often was considered the shading is just denoising, right? So you have a full observation noising. The only thing you do, you just denoise them and you get to the attractor.
They're marking on the manifold. Like
Exactly.
Yeah. Okay, thank you. Now it's clear.
Thanks. I think we can close the questions now. We'll move to the last speaker of this morning. I'd like to call Nazanin Abedini.
So
stop sharing.
Sorry.
Here.
Yeah. It's there. I messed up with your system.
No, that's okay. If you go back to here.
Here. No,
this
here.
one.
Oh yeah.
That. Yeah. I got it.
And now sharing.
Yes. Stop sharing.
Hello. Control L. Oh, no. Yeah.
Is the microphone working?
This thing.
Speak louder.
1, 2, 3.
Is it working?
Can I mute it or not?
Doesn't seem, no.
Just have a look.
Button mute.
Yeah, you see it. Here's the button. Say something.
It's synced?
It's better.
Okay, thank you.
Listening? Yeah.
Yeah.
Floor is yours.
Thank you so much. First of all, I want to thank you for giving me this opportunity to present my recent work. I'm working on a variational type of data assimilation and obtain some theorems for convergence properties of Gauss-Newton iteration. So in this talk, I will discuss about what is the data assimilation framework, what are the observations and data measurements, what are the existing variational methods, and I give my main results, theorems, and at the end, I show you the numerical results. So, assume that we want to forecast the weather, and assume that the blue line is the reality, and the yellow line is the model. So the square, the yellow square is the model forecast. It's the short-term model forecast, and the blue dot is the observation that we have at each time step. So the goal is that to find the analytic solution based on these two information, such that the distance between this analytic solution to the short-term model forecast, and also the distance between this analysis solution to the observation will be decreased. So the one way to show this is this Gauss function, which V is the background error and R is the observation matrix. So consider the general nonlinear problem. We are working to the discretized version of this. We use Euler-time discretization for this nonlinear problem. We have some assumptions. Assume that the bold X be a true solution of the dynamical method, and presume that it's unknown. And also suppose we are given a sequence of observations yj related to each of these x truths at time j, which h is an observation operator that map the space of state to the space of observation. And this noise comes from the normal distribution. And the goal is looking for the approximation solution such that the distance between this approximation solution to the true solution goes to the 0. So the approach that we have chosen is variational type methods. Here I want to review some existing variational data assimilation methods, which these methods leads to the minimization of a cost function involving quadratic forms based on the two information that we have. That one of them is the background solution and the other is the observation that we have. For example, in 3D variational, at each step, we have background solution and observation. So based on these two information, we estimate the solution of the dynamical system and use it to the model because it assumes that the model is perfect, which means that there is no noise in the model. And for the next step, we use that solution of the model as a background solution for time k+1. But for the variational, it contains all this information in the whole time domain and tries to find the best initial condition for this time domain, such that the solution at each time steps are in this equation. So which means that there are no noise in the model, and as I told, X is background solution, B is background error covariance, and R is observation or error covariance. Also, there is another variational method that when the dynamical model is imperfect, the cost function contains an extra term, which shows how the error can impact on the cost function, and Q is the model error. So it's obvious that a U does not have to be exactly a model trajectory. The way that look at this variational method is to look it like a least square problem. And so assume that we have this nonlinear least square problem, and we want to find the minimization of that. If we have a model f of t and x and y, the observation at each time step, and we define f of x, the distance between these two information, the solution of formula 3 gives the best model fit to the data in the sense of minimum sum of the square errors. So how does it work? There is a theorem, is that if f is a nonlinear twice continuous differentiable, if we denote the Jacobian of the function f by j, then the gradient of x is given by this formula. There exists x star such that the j of x star transpose time f of x star is 0. The Jacobian matrix of jx star has full rank n. Then if we have these conditions, the stationary point of phi is equivalent to solving just the gradient equation. So how can we solve this gradient equation? The one of the famous one is the Gauss-Newton iteration. What is the Gauss-Newton iteration? The Gauss-Newton iteration or algorithm choose an initial x0 such that then solve this the first equation and set the next step like this. Yeah. And repeat this procedure until convergence. But there are many papers to look at this Gauss-Newton algorithm. It depends on what is J. For example, we want to, if our cost function is just dependent on the observation operator, and we know that always the observation are sparse and noisy, so this matrix will be imposed. So the inversion of this matrix does not exist. So what other people do? The most famous work is to add some alpha and regularize this coefficient matrix, or add some condition in this inner loop to can cover this problem. But what I will do is that I'm looking to the minimization problem so that my goal is to find the approximation solution that be a solution of a dynamical system. So I try to find a solution to make this distance go to 0 and also stay near to the observation at each time step. So I define this Gauss function and add some weighting parameter alpha to this Gauss function, which has a very important role
in my convergence theorems. And I will show you how can I choose this alpha and what are the sufficient conditions to make this iteration to make the iteration converge to the true solution of dynamical model. So based on Gaussian iteration, I start with some arbitrary initial guess. And this is my Gaussian iteration, which K denotes the index of the iteration. So as I said, I choose J like this. This is the discrete version of my dynamical model. And the J prime is the Jacobian of G, which has this block structure. And we know that the J prime T times J prime is it doesn't have full rank. So it causes problem if I want just to invert this part. So first of all, I assume that my observations are noise free, but still sparse, which means that they are coming from the true state without noise. So the gamma is 0, but they are not identical. The matrix is not identical. So I have this theorem. If the observations are noise free and the error, the initial error is less than 1, and the Jacobian of G, the G prime, is Lipschitz condition, and this is very important condition. And this norm is constant with a lambda. That's a lambda is less than 2 over L2. Then I can then the sequence UK converge to the full solution X. So the question is that how can I find this alpha to make sure that this condition is satisfied. In numerical, I just at the first step I just assume that alpha has a very small value. Then I check this condition for first iteration. I know what is lambda. It's some value less than this one. G prime H, all of these are known at iteration, at first iteration. And I raise alpha. The alpha 1 is 2 times alpha to see that when this condition will be held. As I found the proper alpha, I use it for the next iteration. So there is some sketch of this proof. If I define EK, the difference between UK and X, and write Gaussian iteration for that, and then use this two fact because X is true solution, so the G of X is 0, and use this information for observation. Then use a mean value theorem and Lipschitz condition on G prime and G prime, and this condition that I had in my theorem, I will get to this bond for EK. And as you can see, I assume that E0 is less than 1 and lambda is less than 2 over L2. So as I increase K, this will be 0 and I have convergence. But how about the noisy observation? What happens if we have noisy observations, which means that here gamma is not 0? So I have another theorem. The initial guess is the same. It should be less than 1, the initial error. G prime should be Lipschitz function. And I have another condition on this norm. And then I prove that this distance in L2 norm is bounded with this bond. So now I want to show my numerical results on these two theorems. I work with Lorentz 63 and Lorentz 96 model. This is a Lorentz 63 model. I discretize this with forward Euler method with time step delta t. And I do the experiment. I did the experiments on the for the Lorentz 63 with delta t 0.005. Gamma is 0. And what is the observation? Observation, as I told you, are assumed to be sparse and here is noise free, so it's just sparse. So it means that here, for example, for this example, I assume that I just see the first component of the state. Because the state dimension contains x1, x2, x3, so I assume that I just observe x1. So the observation matrix is just 1, 0, 0. So I compute the error, the L2 error, and the post function. Let's see what happens. This is the L2 error for 100 assimilation. This dashed line is the median of them. As you can see, after 20 iteration, I have the convergence results. And I was curious about the to see the impact of alpha in the post function. Because as I told you, I choose the first value of alpha that satisfy in that condition. But it's obvious that other value after that, this first alpha is also satisfied in that condition. But what happens? Which alpha is the best or is a good choice for us? Each of these lines are the median of the 100 assimilation for L2 error. I can see as I increase alpha, I need more iteration to get the convergence result. For noisy case, again, I assume that the observation matrix is sparse, but it is noisy with this level. Here I can see that the L2 error is bounded. This is the bond that I obtained in the my theorem 2. And I see that as I decrease this noise level, this dark in blue is corresponding to the noise level 10 to the power minus 12. So as I decrease this noise level, I have a convergence result. But for example, the first one is correspond to when gamma is 0.01, and this is around 10 to the power minus 2, but still bonded. I also compare it with constraint for the VAR. So this is the class function for the constraint for the VAR. Q is the model error and R is the observation error. This is the assimilation window is for 25 days. I can see that the Gaussian iteration outperforms this the constraint for the VAR. And The first one, the left hand picture is error for observed, just observed components. What happens if I just looking at the error of observed components, and here is the error of non-observed components. So I can see in these two cases, our approach outcome outperforms. We constrain for the back. And also I use a Lorentz 96 model with 40 dimensions and forcing term 8. I assume that H is not identity. Here in this picture, I assume that I just have 20 observations. So every second step, I have observation, not every step. Here we can see that I have the convergence result. This middle picture is corresponding to what happens if I change the size of observation. So the purple one is the case that I just have 20 observations, and the green one is the case that I just have 8 observations. As you can see, for 8 observations, I need more iteration to get the convergence result. And I also did this for 5 or 6 observations, and I couldn't find the convergence result because I couldn't find the proper alpha for that condition that I had in my theorem. Again, I assume I obtained the post function result for different values of alpha, and as you can see, as I increase alpha, I need more iteration to get the minimum of the post function. Again, I compare Lorentz 96 with constraint for the VAR, and I see that this Gauss-Newton iteration outperforms the constraint for the VAR. And the time domain is for 5 days. Yeah. The summary and outlook, I presented the Gauss-Newton method for solving the nonlinear least square problems. I derived the convergence theorem based on 2 conditions for a noise-free observation. I also derived boundedness for approximation solution in the case of noisy observation. For the future work, I'm looking forward to obtain a bound or some condition to the observability of the observation matrix, how much we can actually observe. Because as you can see for Lorentz 96 model, if the observation size is less than 8, I do not get to the convergence result. That was my presentation. Thank you.
I see already 100 from Francisco. Hi. I have a question between slide 10 and slide 19. In slide 19, I think you made a comparison between weak for the bar and the method, right? And can you also go to 10? But not sure I see the difference. I mean, when I saw slide 10, I thought, okay, this is weak for the bar.
Yeah.
Yeah.
Okay. Yes. Here, a g of u is not necessarily 0, but here I also have the parameter alpha,
which though can go inside norms.
No.
No, you cannot play with the norms. Okay.
It's L2 norm. Yeah.
You could take 1 over alpha, and since that represents, if you want, your
as I can say, covariance in the forcing term, right? In for the variable, 1 over alpha here would play somehow a similar role
with the model error.
With the model error, yes, with your prior, how do you say, trust on your model. Because you can see as a model error, but you can also see it as a forcing term, this J of u.
Yeah, I just assume that's like a regularization parameter for the observation parts. And I assume that the model error here is identity. And play with this alpha to make sure that I get to the convergence or not, based on the condition. But you're right, yeah, we can see also in that way that if I divide it by 1 over alpha, this is the model error. Thanks. Yeah.
What's another hand up?
Thank you for your talk. I'm really happy to see someone presenting variational method in this workshop. And a comment for his question. For the alpha, is alpha constant? It's not constant at all.
Alpha?
Yeah.
At first, it's not a constant.
Yeah.
Because I assume initial value for that. Then, because I have this condition, for this condition, I need to find the proper alpha to satisfy in this. So it's not any constant.
Yeah, that makes sense because if it's constant, you can put alpha inside and all.
Yeah.
Yeah. And my question is, I have a small question about your cost function, your 4D cost function. It might be just a typo, but just.
Yeah.
For the 4D cost function, earlier slide. Yeah. So you write in 4D for R matrix, you didn't show some subscript. Are you implying you are using the same R matrix for each time step? Oh.
For 40 bar? I didn't get.
Yeah, so in your 40 cost function, in the second part,
yeah.
you have R matrix, R inverse matrix, right?
Yes.
For the observation error covariance
Yeah,
matrix.
exactly.
And you didn't get some subscript like J. You have YJ, but you use R here. You didn't show some subscript for J. So it might be you are implying that you want to use the same R matrix for each time step. Am I right? Or it's just a typo you actually want to write J in there?
I think it's a typo.
Yeah.
Because for each time steps we have this error covariance. Yeah.
Yeah, I mean it's fine in Lawrence analysis, Lawrence models, yeah, but in reality, they usually have different alpha, different time steps.
Yeah.
Just to clarify.
Yeah. Thank you.
Another question, Sam?
Can you go back to your theorem, please?
Which?
One of the theorems, so even the first theorem or the second theorem. But anyway, I just want to say that I really appreciate that you make an effort to prove something. That's great.
Yes.
But I actually want to provide some practical comments here. In practice, getting the Jacobian G prime is already infeasible for complex or practical problem, right? Let alone showing it is Lipschitz continuous. And then finding the Lipschitz constant level 2 is almost impossible, right? So when you say, you already know L2 impact, in practice, you may not know. And for practical problem.
I found the Lipschitz condition for Lorentz 63 and Lorentz 96.
Yeah, but that I think it's similar enough for you to do. But in general, one you may not be able to do so. And then you actually want to be aware that in that case, your condition lambda less than 0 or greater than 0 less than L2 over 2 may not be approachable, right? Because you don't know L2 and at all in general.
Yes, in
Okay.
more complicated examples.
Yeah, and the second
Because it
com-
depends on the Lipschitz condition, yeah.
Yeah, the finding Lipschitz constant is very difficult. I mean, especially for large scale complex problem. And the second comment is that you assume that the matrix G transpose G, G prime transpose G prime plus alpha H transpose H is invertible, right?
Yes.
Because otherwise that does not make sense.
Yes,
So
yeah,
in-
exactly.
In general, you notice that the token G prime change from one place to another because a function of X.
Yes.
Assuming that matrix invertible require.
Yes, it's required to the choice of alpha. If the alpha is greater than half, this will not be.
In general,
yes.
No, it's alpha constant you cannot do, so already depends on H and depend on the.
Yes, exactly. If the observation, the size of observation, for example, in Lorentz 96 is less than 8, this matrix is not invertible.
No, I'm saying that's in general, this matrix, regardless of what alpha is, the matrix may not be invertible because because that matrix invertible or not, it depends on H and G prime.
Yeah.
Right.
Yeah.
So so alpha just makes you can tune the alpha, but alpha may not be able to help you with the invertibility in general. Okay, I mean I can talk to you more later because these are two matrices. If they don't, they have you have certain conditions, actually very strict condition in order for the combination to be invertible. And alpha is just a tuning parameter will help if the matrix is already not invertible, the summation. Yeah, but anyway, it's just a great effort. Thanks a lot.
Thank you.
Thanks. I think we can give a round of applause for all the speakers coming. If you were good grinning, someone deserve a lunch.
Can I ask a question? Is this room going to be locked or can we still show posters?
No, this is the last. No, it's 3 years of today.
But can the posters remain in there, or do you need to move out the posters?
No, we have a room.
No.
The room will be open and
The
nobody.
posters can stay here.